This is the second video on uncertainty. Now, in the first video, we demonstrated that open loop control cannot deal with uncertainty, and therefore where there is significant parameter uncertainty or disturbances, open loop control is inadequate. But you might be confused because you might think, well, humans deal with uncertainty all the time and we're quite good at it, so there must be a simple logical solution for an automated control system. So what is it that humans do? Well, this is what we do. We monitor and correct. That's key. Humans monitor and correct. Oops, I don't know what's happened there. We observe the output and, if necessary, make corrections to the input. So what we need to do now is draw a flow diagram to demonstrate the flow of information when a human monitors and corrects. And by understanding the human process, we'll begin to see how we can automate this. So what I'll do now is I'll draw this flow diagram of information. Let's imagine we've got a process. Here it is, G. It's got an input U, and it's got an output Y. Now, what do humans do? You're going to have to excuse my sketching being somewhat imperfect. But anyway, here we go. So there's our human, a very happy person indeed, or perhaps not. Okay. Now, what this human is going to do is he's going to monitor the output. So you can see I've used his eye, he's looking at the output and he's saying, what is this output doing? Okay, is it doing what I want? So this observation or this monitoring is a key step. Now, what else is going on? Well, there is also coming into the human brain information about the target. What do I want the output to do? And the brain is then saying, okay, I know what the target is. Somebody's given me that information. I can see what the output's doing. So now what I need to do is select an appropriate input in order to make the output do what it wants. And this is where you get the concept of feedback. So what you've got is you feed back the value for the output. There's the feedback path. That's the monitoring process. And then you have a decision which closes the loop. Okay, so you do something with that feedback which then goes on to the input and affects the G. So there's a classic feedback loop. Now, how would we write that in terms of a block diagram? I'll squeeze it in the bottom here so you can see. So you've got your G here with Y going out. You feed back the Y, and here's the key point. What you're going to do is you're going to compare that with the target, R, and that gives you an error. What's the difference between the target and the actual output? So that's the monitoring process and the comparison with the target. And then what you do is you come up with a decision. So I can't write it all in there, but if you imagine that box says decision, and that decision says, given the error that I've just observed, what input should I choose into this process? And you'll see that this is a continuous loop. So you're continuously monitoring the output, generating the error, making a decision, modifying the input. Okay, and therefore we have our standard feedback loop. Now, the argument we're going to use here is this is how we deal with uncertainty, because if uncertainty has any impact on the output, then we notice that in the monitoring process and we make a decision to take account of it. So the role of feedback. Okay, just to illustrate how we might do it and that it's effective. If you imagine you're driving, then when you drive a car, you continuously monitor the speed of the car. You don't want to get a speeding ticket for a start. Okay, and in line with that monitoring, you are also continually making small corrections to the accelerator to ensure that you have accurate speed control. Now, the interesting thing is that this seems to work no matter what car you are driving. So you could get into 2, 3, 4, 5 different cars, very different masses, very different powers, and yet you're still quite effective at controlling the speed. Okay? And it's this monitoring and feedback mechanism which allows you to do it. So even though your knowledge of the model of the car is somewhat imperfect, you still manage to control speed very accurately. Now the other interesting thing is you could change the road conditions. It could be a bumpy road, a smooth road, any sort of road. It could be going up a hill, could be going down a hill. You could be into a wind or with a tailwind. No matter what the uncertainty, we are very effective. Okay, so we're very effective at control, and it's this monitoring and feedback which allows us to do it. Okay, now you can come up with a number of other examples which we won't do here to save time. So hopefully you're reasonably well convinced that this concept of feedback is what we need to deal with uncertainty. And we've also shown you that an automated way of doing this would be to represent it using a block diagram a bit like the one you've got here. So you've got a feedback path from the output. Okay, so that's the monitoring. And then you've got what we call a summing junction, where that's actually a comparison between the target and the output. And then in here you've got a control law, okay, which says, given the information I've got about the error, what do I need to do to choose the input? And obviously this G represents the process. Now what we want to do is show next, if I introduce a bit of uncertainty into this loop, so I say, well, I don't know G exactly, okay, or maybe there's a disturbance on the process, what impact will that have on the behaviour of Y? First of all, we might need to ask, how do I represent this uncertainty? We're just going to use two different types of uncertainty. So we're going to say, with parameter uncertainty, instead of having just G of S, you may have G plus F of S. So your model is slightly different. You'll assume that in general F is small compared to G, but it represents the fact that the parameters may be imperfect, not known exactly. If you have a disturbance model, then what you would end up with is a block diagram a bit like this. So you have notionally an output to G of S, which you could assume was perfect, but before you get the real output Y, you need to add on to that the disturbance signal. So you've got Y equals GU plus D. So that's fairly representative of a disturbance model. These are the two types of uncertainty we're going to use next. First example then, parameter uncertainty. And you'll see this is the same as video 1. We have a notional model, 3 over S plus 4, but we're saying that the real system, in fact, is 3.2 over S plus 3.8. And I'm now going to control this with a control law, M of S equals 5. So the feedback loop we've just done, M of S equals 5, and let's look at how the system behaves. Well, if we look down here at the outputs, you can see the model output in blue and the actual output in black. And what you will notice is they're very close. Despite the uncertainty in H of S, the resulting output responses are very close. Now, we've given you the input responses over here as well for completeness, but we're not going to discuss those particularly here. So what can I say? Here we see we've put up the open loop responses that you saw in video 1. So what you might want to look at is what gap did we have between the responses when they were open loop, and you can see it was quite a big gap when you're doing open loop. Now that we've closed the loop, the gap between the two responses is very small. So this feedback has dealt with the uncertainty far more effectively, and that's because of the monitoring and the correction. In summary, we've reduced the sensitivity to the uncertainty by introducing feedback. Here's example 2. So in this case, G of S was 3 over S plus 4, S plus 1, and H of S 3.2 over S plus 3.8, S plus 0.9, and again a control law, M equals 5. And once more, if you look at the output plots here, you'll see the difference between the two output plots is quite small. So the closed loop is less sensitive than the open loop in the presence of parameter uncertainty. And that's why we introduce feedback, isn't it? As soon as we introduce monitoring, we expect to be able to reject uncertainty to some extent, and that's what you're seeing. Now, go back to example 1, and this time we're going to introduce the disturbance rather than a parameter uncertainty. So we've got our G again, there it is, 3 over S plus 4, but now we're going to say the output is given by GU plus 0.2 over S. So we've specified the magnitude of the disturbance to make things clear. The magnitude is 0.2. So again, you look at these two plots here, and you say they're actually quite close together. Now, if you remember what was done in the first video, when you have a disturbance in open loop control, the disturbance is 0.2, then the gap between the two plots is the size of the disturbance, 0.2. I've marked it with an arrow. So you'll see the gap in the open loop is much, much bigger than the gap that we've got here with the closed loop. So again, by introducing feedback, we seem to have rejected the disturbance far more effectively. Okay, so again, you see we've reduced the sensitivity to disturbances. For completeness then, here's example 2, the second order model. Again, I've used a disturbance of 0.2, and again, you can see the gap between the two outputs is very small compared to 0.2, which was the size of the disturbance. So in summary, introducing feedback, now I've emphasized a word here, can reduce sensitivity to uncertainty. Please don't assume that any feedback will help. If it's not a well-chosen feedback, then it could be a disaster. But introducing feedback can reduce sensitivity to uncertainty. And what do we mean by sensitivity? In essence, we mean the relative change in behaviour when uncertainty is introduced. Okay, so what's the ratio of the outputs of the model and the uncertain system? However, feedback on its own is not enough. Now, we didn't emphasize it a few minutes ago, but if you go back and look at those earlier slides, you will find that in none of those examples did we actually track the target. We didn't mention that because it wasn't a key point, but none of them track the target. So introducing feedback on its own doesn't necessarily mean you'll get good tracking. Okay? It also doesn't necessarily mean you'll get good behaviour. We didn't look at the transient behaviour. So where are we? We also need to ask what constitutes effective feedback. And effective feedback needs to handle uncertainty and obtain good performance. The purpose of this video was simply to illustrate that if you want to deal with uncertainty, then you will need feedback. How you design it is the next step.